Welcome, sir. I am Dr. Kalyani, Assistant Professor in the Department of Mathematics and Statistics. Warm greetings to everyone who are presented on the event of Faculty Development Program on Innovations in Machine Learning, Artificial Intelligence, Data Science and Modeling, organized by the Department of Mathematics and Statistics in collaboration with Department of Electronics and Communication Engineering, supported by the IIT Roorkee. I take pleasure in introducing the speakers of today's hands-on practice session, Dr. Sujit Kumar Das, Assistant Professor in the Department of Computer Science and Engineering, NIT Warangal. In the morning session, Sir has given a talk which helped many participants to understand about the multi-objective optimization and its applications. Now, Dr. Sujit Kumar Das Sir will make us to expertise on multi-objective optimization through this practice session. Sir, can you please?
Yeah, thank you. So am I audible? Hello?
Yes, sir, you are audible.
Okay, thank you. So once again, I would like to convey my sincere thanks to the conveners, co-coordinators, and co-conveners, and more or less all these committee members for this international workshop on innovations in machine learning, artificial intelligence, data science, and modeling. So which is organized by Department of Mathematics and Statistics in collaboration with Department of Electronics and Communication Engineering, Vignan's Foundation for Science, Technology and Research. So really it's a honor or it's a privilege for me to share my thoughts on this nice platform. As morning we discussed regarding multi-objective optimization and discussed some theoretical ideas, as well as we shared our thoughts regarding how to implement this NSGA2. So I told something regarding how to implement that non-dominated sorting, as well as how to implement this crowding distance. So in this session, so it is actually 2.5 hour session. We will proceed up to 8 o'clock. So what we will do that we will try to implement both the single objective and multi-objective optimization using this Python programming. Initially, we will start with this single objective optimization. Quickly, I will show you that how to implement, how to solve one very simple problem using this Python programming, okay, in the context of genetic algorithm. Then slowly we'll be moving towards this multi-objective optimization. Now, what I can tell before proceeding that participants, those who are familiar with Python programming, maybe they will feel comfortable here. And for other participants, again, I will try my best so to deliver my thoughts from the basic level, so that also you can be benefited. Now let me share my PPT, as well as I need to share my program. So firstly, let me share my PPT. So here, what I will show. Okay, just 1 minute. I think I will just share it. Yeah, I will share it. Just 1 minute. So my PPT is visible. Anyone can respond?
Yes, sir, it's visible.
Okay.
Yes.
Okay. Thank you. So firstly, start with this implementation of genetic algorithm using Python, so that things will be very clear. So the entire thing I'll be covering using this Google Colab platform. So where I'll show the Python coding. So we'll try to understand. We are trying. So here we will try to maximize the output of an equation. Okay, we'll take some equation and we'll try to maximize what will be the output for this equation using Python programming and applying this genetic algorithm. Now see, so this is a sample kind of equations we have taken. So this x1, x2, x3 all these are our data. So that means we have now 6 data points. Okay, x1, x2, x3, x4, x5, x6, 6 data points, and each and every data point is associated with some you would see this is a we want to maximize output this function, but we want to maximize the value of y. So here the value of x1, x2, x3, x4, x5, x6 will be given. We need to optimize the values of the weights w1, w2,
Excuse me,
w3.
sir. Sir, your slide is not moving, sir.
No, I'm not moving the slide, so I think
Okay.
just one by one bulleted points it is coming. Now checks the this bulleted point it is showing.
Okay, sir.
Yeah.
It's okay, sir. No, sir.
Okay. So actually this equation has 6 inputs, as I told, x1 to x6 and 6 weights. I think you can contact with your coordinators if you are finding that what I am telling sometimes it may not be visible. So actually I am using some pen here. I am trying to highlight something using red color. I think you are getting what I am highlighting here. Are you getting here what I am writing or what I am highlighting using my pen? I am using a writing pad, so
Yes,
using a
sir. Yes,
pen
sir.
to highlight. Yeah, okay, thank you. So for here we have taken this input values x1, x2. So these values are known to us. What you need to do? So we need to find out the parameters. Parameters means nothing. These are the weights. Okay, that will maximize the equation. Now it's a very trivial, very simple problem. Some values are given. Okay, some input values are given, and some weights are associated with each of the input values. So what is our objective? Objective is we need to optimize the weights so that we can maximize the output. So that is our objective. You may find it, sir, this is very simple one because I know once since we have taken 4 minus 2, 7, 5, that means which are the positive weights. Okay. So for the positive weight, you multiply with this largest possible number, and for the negative weights such as minus 2, you multiply with the smallest possible negative number. That will solve your problem. Why you want to apply genetic algorithm kind of things to solve it? Yeah, actually we will see here. Okay, we will test it. What is our thought that okay, largest possible number multiply with the positive input. Okay, smallest negative number multiply with the negative input. How actually this kind of thinking will come from genetic algorithm? That is the success, or that is the powerful nature of genetic algorithm. Whatever you are thinking, exactly same thing I think we will get once we will apply genetic algorithm. So that is only our task here. So this is our equation input. We have taken 4 minus 2, 3.5, 5 minus 11, 4.7. Okay. And see here, how many number of weights we are considering? 6 weights we are considering. You can consider these are our weights. These W1, W2, W3, W4, 5, 6. So these are our weights. So 6 weights we are considering here. Okay. So what is our next task actually? So once we are starting with this genetic algorithm, so our task is to build up the initial population first. So we will define the initial population. So once we want to design the initial population, as you know, this initial population will be consisting some set of solutions. What does it mean? So each solution means one chromosome. Each candidate solution means one chromosome that I told in the morning session. Now, here is chromosome having how many genes? What will be the size of the chromosome? Size of each and every chromosome will be 6. It will contain 6 genes. So what is the gene values? One gene means one weight. One gene means here you are considering one weight. Okay. So then you may consider, okay, then how many solutions will be there in the population? How many solutions we will consider in the population? Actually, that sometimes it may vary. So here we need to consider 20, 30 and some number of solutions for building the initial population. Okay, now let us come to this Python programming side. Then it will be much more easier for me to explain and for easier to you understand also. Now see here. So I hope my screen is visible. I am trying to show some Python programming. I hope this is visible. Okay.
Yes, sir.
Okay.
Yes.
Now see, so this is our equation input. See, this 4 minus 2, 3.5, all these are equation inputs. Okay, these are equation input, and this is the way to write in Python, as you know. Simply you write equation inputs, this it will come equation inputs. As I was mentioning in morning with some of the discussion with some of our faculty members or colleagues, that Python programming is much more easier in comparison with other programming. And believe me, if you are stronger in C, C++ kind of programming, then Python programming is going to be very much easier for you. Okay, so this is our equation input. Now this is our number of weights. How many number of weights we need to consider? 6 weight. Okay, since 6 inputs are here, 6 inputs. So number of weight we are considering 6. Now see, solution per population. For the sake of simplicity, I am considering only 8. That means per population, 8 solution will be there. One solution means one chromosome. What is the size of the chromosome? Size of the chromosome will be 6, which is number of weights. Number of parents mating. So here I have considered it is 4. That means later I will show you that I want that 4 number of solutions should take part in this crossover process. Now see, here I am writing population size, solution per population and number of weights. So I am trying to define some matrix here. Population size, see, it is 8 by 6. That means what? 8 number of rows will be there. Each and every row, 6 number of columns will be there. Why 8 rows I am considering? 8 rows I am considering to represent these 8 solutions. Because I am thinking that in my initial population, 8 solution will be there. Where size of each solution will be 6. That means in each of the solution means chromosome. So in each of the chromosome, number of gene values or number of weights will be 6. Then we need to import NumPy. As you know that NumPy, pandas, all these are very essential things in Python programming. NumPy means it will help you to compute all these numerical kind of things. Since it's all about numerical and sometimes it's all about data, so we need to import, I think, import pandas and NumPy once you are writing this Python programming. So here I am using NumPy. Okay, let's see. So we are importing NumPy. Now see here, see importantly, so here what I am doing, new population, what I am writing, just check. New population equal to NumPy dot random dot uniform, low equal to -4, high equal to -4, size equal to population size. What is my population size? Population size is 8 by 6, 8 row, 6 column. I think you are perfectly getting why I am telling it is 8 row, because solution size I have fixed actually. In my initial population, 8 number of solution will be there, where size of each and every solution will be 6. Okay. Now, why I am doing that? As you know, for any meta-heuristics techniques, we need to start with the initial pool of solutions, which is randomly generated. Here, I am not utilizing any tool, any machine learning or artificial intelligence tool kind of things to initialize my initial population. But simply, I am randomly generating my initial population. Where you see, here I have written that low equal to -4.0, high equal to 4.0. What does it mean? Low equal to, that means in that range, -4.0 to +4.0, whatever value I will get, that will be belonging to my initial population. See here, if I run it, then what will be the output? Just check it. Check it. So how many rows are there? So if you check whatever I'm highlighting there right now, you will check eight rows are there. That means 8 solutions. Okay. And each and every solution, see, these are the values. Values means first value belonging to W1, second W2, third W3, W4, W5, W6. These values will associate with each of the weights. Okay, so initial population we have generated. Up to this part we have completed. Now here I have taken something, population dot shape. New population dot shape means it will give you what is the number of rows. New population dot shape 1, it will give you the number of columns. Okay. So once I generated that initial population, then what we need to do? Then we need to compute the fitness function for each and every solution. As you know that fitness function will define the goodness or quality of a solution. So we need to compute now the fitness function values for each and every solution. Now check here how I am computing the fitness function here. So if I go back through my slide, then what will be the fitness function here? Check. So in fitness function, simply this is your fitness function now. Simply will be multiplying weights with the particular given input values. Weight with the input values that will multiply and ultimately will add it. We'll take the summation. So that will be our fitness function for it. Because here our objective is itself to optimize or to maximize this function value, to maximize the value of y. Okay. Now check it here. How I am doing that? Check whatever right now I am writing. Just check. Fitness equal to I am writing. See numpy dot sum. Okay. New population into equation inputs x is equal to 1. What does it mean? What is your new population? So this is your new population. Check it clearly. Whatever right now I am highlighting, this is my new population. Okay. New population into equation input. What is your equation input? Check it. So this is my equation input. These values are my equation input. Okay. So we will multiply this equation input. Okay. Equation input will multiply with the new population. And as you know, what does it mean? New population means what? In new population, we got some random values for weights only, na? New population, we got some random values for the weights. Okay. So new population into equation 1, x is equal to 1. X is equal to 1 means row wise it will do that particular multiplication and then it will sum it up. So I will make it much more clear. So this value will be multiplied by data value 1. Second weight W2 will be multiplied by x2. This multiplied by x3. This multiplied by x4 and so on. What is the value of x1, x2, x3? No need to say. So this is the value of x1, x2, x3, x4, x5, x6. I think now it is clear that how we are finding this, how we are finding the fitness value for each and every solution. Okay. First solution, first row, fitness value will be this. Second solution, second row, fitness value will be this. Third solution, fourth, fifth, sixth, seventh, eighth. See here. So for all those 8 solutions, we are getting 8 fitness values. As I was discussing with some of the colleagues in morning session that how Python programming is becoming very much easier for us. Now see here. So if you want to do the same thing using C, C++ or Java programming, then how many number of lines or coding you need to write? And here what you are doing. So like writing only one line of code and everything is getting generated. So this is the powerful kind of nature of Python programming. Actually, Python and MATLAB, both these things are equivalent only. MATLAB is also very much powerful, as you know. But normally we use Python because, Python is free version and MATLAB is licensed version. That means, okay, universities, very big universities like this Vignan's university, we may have that MATLAB version. But at the same time, many of our participants may not have the licensed version of the MATLAB. That's why often I am preferring to discuss using Python programming. But again, the same thing we can do using MATLAB also. Okay, so we are getting the fitness value for each and every solution. So fitness value we are getting. Okay, so next what we will do. So once we are getting the fitness value of each and every solution, next check what we are doing here. Here, just check what we are doing here in this particular case. See. Now, so after once that is over, once we are finding the fitness value, then we want to select some set of parents. Now selection will come. Okay, why selection will come? We want to select some set of parents where we apply crossover and then we'll go for mutation. So once we want to apply crossover, so before applying crossover, we need to apply the selection process. Now see here I have not applied any kind of traditional selection process, but to make the process simpler, I am using some simpler coding here. What you have to do, just check numpy.empty parents equal to numpy.empty number of parents mating new population shape 1. What is number of parents mating? Initially, I think I have written number of parents mating, that is 4. That means we want that 4 number of solutions should take part in the mating process. Mating process is nothing is here in the technical term. This is your crossover only. Okay. So number of parents mating, this is 4. And what is the value for this new population? New population shape 1. As I told you earlier, that what is the meaning of shape 0? Shape 0 means it will give you number of rows. Shape 1 means it will give you number of columns. So this is shape 1, number of columns. Check it. So it will give 4 by 6. That means, see, number of parents mating, it is 4. Now new population, what is new population shape? So actually you will find out here value will be 6. So that means what it will give? Okay, what it will give here? So I want to make that 4 by 6. Initially that, see, initially we worked with a matrix. Matrix was 8 by 6. That means 8 number of solutions where size of each and every solution was 6. So here from 8 by 6 solution, I want to convert it in 4 by 6 solution. Why 4 by 6? Because here 4 I am only defining it. That very precisely I am defining it for to make the process simpler. I want that from the set of 8 solutions, you need to find out 4 solutions which are much more better. Okay, that process I am trying to do here. You might feel here I am not implementing natural selection. Yes, correctly, I have not implemented any natural selection here. To make the process simpler, I am doing that. Okay, so out of 8 solutions, I need to consider 4 best solutions. That is my target. So what I am doing? Initially, I am making parents empty. Okay, that where I will keep the 4 best solution. Initially, that location, that matrix I am keeping empty. That's why I am writing numpy.empty. Okay, next. For parents, this is the for loop actually in Python programming. For parents, see, for parents number in range, number of parents mating. What is number of parents mating? It is 4 only. That means, so it will this for loop will be iterating for 4 times. So this is the syntax of for loop. Next, what I am doing? So something here I have done. So here meaning is that, see, initially I will find out the maximum fitness value solution. I will find out the solution which are having the maximum fitness value, what I am writing. And what I am to do, I am finding the index of that solution which will have maximum fitness value. See, max fitness index, numpy, where fitness is equal to numpy dot max fitness. What does it mean? Numpy dot max fitness means it will select the maximum fitness value. Okay, and in that fitness value, what is the index? Each and every solution having some index. That means first solution, whatever I'm writing, maybe index 0, second, like an array concept only. Second index 1, third index 2, and similarly others. Okay, so index I got. Then what I am doing? So in that index, okay, in that index, what are the solutions? In that index, what are the various values for that particular solution that I am thinking, that I am doing here? Okay, so this parents, this is the statement. See, what is maximum fitness index? So it is the index of that solution which is having highest fitness, better solution. So that solution I am keeping this inside parents. Parents, this. Parents number means what? Initially parent numbers will be 0 because here it will start from this 0, then slowly it will be moving 0 to 3. Okay. So are you getting? Then that means parents 0. Initially I am copying which is the best solution. Then see what I am doing. For the best solution, here I am giving something that fitness, max fitness index equal to this minus. Why? Because this is a logic only. Because in the next iteration, I want to avoid the maximum fitness solution which you have already included in your parents. Okay? So I will find out the next best solution. So I will get the next best solution using this logic. So in this manner, I will get 4 better solutions from that particular new population. Whatever population you have created from that population, here I will collect 4 better solutions. Okay, now see here. So this is my 4 better solution, whatever I am getting from my new population. Are you getting? Initially, we had the population size 8 by 6. From those 8 by 6, we are collecting 4 solutions where all the solution fitness value is much more better in comparison with the others one. Okay, so that we are doing. Now, if you check it, you will get it how the things are coming here. So, if you check with my initial solution where fitness value is maximum, exactly the same thing will happen here. Okay, so here I am finding the fitness value. Now, let us check here what is the highest fitness value. This is the highest fitness value. Which solution it is? It is the third solution. First, second, third. Third solution, highest fitness value is 55. Okay. So third solution, highest fitness value is 55. So which is my third solution? Perhaps this is my third solution. Okay, that means, so in my parents right now, third solution will be my first solution. Let us see, 7799689. Yes, so see that. So this is my first solution. This is 55. Which is next one? Next one will be 34. So if you check exactly same thing we will get, because it is programming, it will not do any mistake. We are the human beings, we can do some mistakes, but once you are working with this computer programming, if our programming is correct, how many repetitions you will do, it will do correctly. Okay. So for first 4 solutions you are getting here. Okay. Next. So this is our equation input. Once again we have given. So next what you need to do? Now just check. Next what you will do? We are getting 4 better solutions. Okay. So here once again I am confirming, okay, whatever the solutions I am getting, let me check their fitness value. It is better or not. Exactly, it is 55, 34, 10 and 9. See, this 55, this is 34, this is 10 and this one is 9. So first 4 fitness value we have now considered here. Okay. Okay, next. Next what we will do? Just check. So now we have selected 4 solutions. So these 4 solutions we will apply in crossover. Okay. So that means here we have 4 solutions. So once we will apply crossover on these 4 solutions, as a result, we will get 4 offspring solutions. In the morning sessions, I told crossover in a pair of solutions we will apply. From those pair of solutions, we will get offsprings as another pair of solutions. That means if 2 solutions will apply crossover, as a result, we will get 2 offspring solutions. Number of solutions will not be changed here. That means here if 4 be our parent solutions, we apply crossover on those 4 parent solutions. So as a result, we will get exactly 4 offspring solutions. Okay. Now here, see. Here I have given that how we are implementing the crossover. See, why I am writing this statement, offspring equal to numpy.empty offspring size. Why I am writing this? So initially offspring I want to make empty. So this is the way that numpy.empty, so that initially offspring will be empty one. What is the size of offspring? You have checked it. Offspring will be 4 by 6 size. 4 solutions where size of each and every solution will be 6. Next. Crossover point. Numpy.this offspring size by 2. So here, whatever we have done, we ensure that crossover point will exist exactly middle of each and every solution. Crossover point will be there exactly middle point of each and every solution. Okay. Now let us see. See here. Here I have implemented crossover in some different manner. How I am doing? Just let us check. This is for loop for k in range of spring size. Okay, for k in range of spring size. So what is your offspring size? 4 only now. Okay. Offspring size 0 means 4. Offspring size 1 means 6. So this for loop will be moving from 0 to 3, 4 times. Okay. Parent 1, we are selecting parent 1 because for the crossover, a couple of parents we need to select. Parent 1, how parent 1 we are determining? Parent 1 index equal to C. K, this modular division, parents save 0. Just check here. What we are trying to do actually. Parent 2 index K plus 1, parent save 0. Here, what I am doing, so initially I will select parent 0, parent 1. Both these solution, index 0, index 1. I will select. Okay. So initially index 0, index 1 solution I have selected because it will be 0 only and it will become 1. Okay. K plus 1, 0 plus 1 divided by this. So here it will be value will remainder will be 1 only. So here we will get 0, here we will get 1. Okay. That means first solution and second solution. We are applying in crossover. See how we are doing it. Check it. Offsprings K, 0 to crossover point. Parents, just check it very clearly what I am doing. These parents, parent 1 index 0 to crossover point. That means in offspring 0, what we are doing? Just check it. Offspring 0, 0 to crossover point, we are selecting from parent 1. In offspring 0, 0 to crossover point. That means first 4 values. First 4 values we are copying from parent 1. And in my this offspring 0 remaining values, that means 5 to 8. First 3 values we will copy in our offspring 1, then crossover point to remaining. That remaining values we will take from our parents 2. Just check it very clearly what I am doing here. As I morning session I showed that crossover is nothing but this exchange of information only. Okay, so 0 to crossover point, as I said, crossover point I took middle of any solution. Here our solution, how many points are having in our solution? Each and every solution size is 3, size is 6. So what is the middle? So middle position will be 3. So I'll request my participants please not to talk. If you have any questions, please feel free to ask. Otherwise, meanwhile, if you talk, then it may be little bit disturbance for me. So I'll request the coordinators or the organizing committee members to please mute the participants so to avoid some unnecessary disturbance. So participant,
1 minute.
Yeah.
Yes, sir. Now, okay, sir. Sir, please unmute your mic, sir. Sir. Sujit Kumar Das. Hello. Sujit Kumar Das, sir.
I think, yes,
Okay.
now I'm unmuted. Hello, am I
Yes,
audible?
Audible,
Okay,
sir.
okay.
Audible.
Actually, I feel that from the coordination side only, once you are muting everyone, my mic is also by default muted. Anyway, it's okay. Yeah.
Sir, if possible, can you increase the size of the window?
I think actually,
Any program
if I increase, okay, little bit I can increase, but I think from the participants machine also they can easily change. They can easily, I think, increase it, decrease it, whatever they can do. Okay. Okay. So participants, so please zoom in or zoom out, whatever you want to do. As you know, all flexibilities will be there with you. So from your end, you can do everything. Actually, here I need to maintain here some size so that font size, all these are related. Yeah. Okay. Thank you. So now what I am trying to say here that we are performing the crossover. So here we have considered the middle point. So here middle point means 3 because size of each and every solution is 6. Okay. So in first offspring, what we did, so from 0 to crossover point, that means maybe from 0 to 2, we took it from parent 1. And 2 to remaining, we took it from parent 2. See here. This is exchange of information only. See, this 0 to crossover point we took from parent 1, and then crossover point to remaining we took from parent 2. This is the syntax for that. What is k? K be our offspring. Crossover point, once we write this crossover point colon this, that means from the crossover point to the remaining. Okay, so this crossover point to the remaining, so it will be copied from parent 2. Now see here how nicely we are implementing the crossover. So first portion we are taking from this parent 1, second portion we are taking from the parent 2. We are getting one offspring. Okay. Next what we are doing, see, so 0, 1 it is over. Next, if you look it closely, carefully, then you will find out 0 and 1. After that, 1 and 2 will be selected. That means first and second. So from the first and second, you will get another offspring. Then second and third parents will be selected. From second and third, you will get another offspring. Then third and fourth will be selected. From third and fourth, you will get another offspring. So ultimately, from 4 parent solutions, you are getting 4 offsprings or not. So that is our objective here. 0 and 1, 1 offspring, 1, 2, second offspring, 2, 3, third offspring, and third parent, and fourth parent, another offspring. So this way we have implemented the crossover. Okay, so crossover is over. Next, what you need to do? So once crossover is over, let me check what about the offsprings I am getting and their fitness value is increasing or not. Surprisingly, here you will find out their fitness value is increasing. Just check it. This is the fitness value. Fitness value on average, it will be increasing. That is very normal. So as we know that once we implemented the selection itself only, we consider better solution. And once we are implementing crossover on those better solution, so probability is telling that average fitness value of your solutions will be increasing. So it is done. So next what we will do? So next we will do with the mutation. Crossover is done. Okay, next we will go for mutation. So here whatever I have done for this mutation to make it simple, just take it. So for index in range, offspring shape 0 means what? Here offspring shape 0 means row 6. So here whatever I am doing, check a random value numpy dot random uniform minus 1 to 1. So here we have considered one random value in between -1 to +1. Okay. Then what you are doing? Just check. Offspring index at position 4. This is offspring IDX means index, 4 means the position. So we are adding the random value. Just check here what I am doing. So I have considered 6 here. I am not using any mutation probability. Here I have considered all those 6 solutions, whatever we got from that crossover operations. Next, what we are doing, we are selecting each and every solution. See, index, offspring shape 0. That means offspring shape 0 means it will give you 4 here. So then a random value, we are generating a random value, and that random value we are adding with each and every solution to change the 4th bit position. Just take it here, 4th position, because as I told, each and every solution right now size is 6. That means for each and every solution you will get 6 values actually. So here 4th value we are changing for each and every solution. So obviously this is a mutation. Mutation, as I told, is nothing but the sudden changes in gene that we are telling mutation. So we are applying mutation here. Okay, we have implemented mutation. So once we have implemented mutation, then once again you will see here that our solutions are changing. Now I will show that how our solutions are changing here. Okay, how our solutions see. So this is our 4th one. First, second, third, fourth means 0, 0. If I start from 0, 0, 1, 2, 3, 4, 5. Okay. Next, see here. This position, it is changing or not? 4th position means index 5. This position changing or not? -2.7. Now it is becoming -2.83. you will see all other values are same only. Check it very carefully. All other values will be same. Before that it was like this, minus 1.99, it is minus 1.99. Only this fourth index, that means fifth position values for each and every chromosomes we are changing. Okay, randomly we are adding some value which is in between -1 to +1. Okay, now let me check the fitness value after mutation. If we check the fitness value after mutation, see, surprisingly again average fitness value is improving. Just check, this is our fitness value. As you know that this is our expression to compute the fitness value. Offspring into equation input, x is equal to 1. X is equal to 1 means it will compute row wise. Once again I am repeating, first value will be multiplied with x1. x1 means our first input. Second value multiplied by x2, third value multiplied by x3, and so on, and then it will be added, summing it up. So you will get the fitness value of each and every solution. Here surprisingly we are noticing that fitness value is itself increasing. This is the powerful nature, as I told earlier, powerful nature for this genetic algorithm. Okay, so fitness value we got it. Okay, now see. Now what we are doing, we are forming the new population. That means, see, in this new population, so what is the right now our population size after implementing the mutation? Our population size is 4. But what was our population size, original population size, before implementing crossover or mutation? Population size was 8. As I told, each and every iteration, number of solution in your population will be fixed one. You cannot change that. So here also you need to maintain that number of solutions should be 8 only. Just check it here. New population 0 to parents. See what I am doing. So 0 to parents safe. That means first 4 solution I am taking from the parents. Remaining 4 solutions, so we are taking from these offsprings. Just check it. So this is the logic for that. This is 0 to parent safe. What is parent safe? It will give you 4. And next, parent safe to remaining. So parent safe, it will give you value 4. So parent safe to remaining. So that you are considering from offsprings. You can ask me, sir, why you are doing that actually? See, why I am doing that? So fact is that once we selected 4 better parents, okay, those 4 better parents was much more better than the remaining 4 values, remaining 4 solutions. Then from those better parents, again we applied some crossover mutation selection and got 4 offsprings. Now if we combine those 4 better parents along with 4 offsprings, so again we are getting total 8 solutions, and here itself solution quality will be much more higher than the earlier one. Okay, so that was the context before that. So this is our new population right now we are getting. Okay, again you compute the fitness value of your new population. You will find out average fitness value will be increasing only. Check how average fitness value is increasing. Once again I am repeating. From our initial pool of solutions, we selected first 4 better solution as a parents. On those parents applied selection, crossover, mutation, all those things, got another 4 offsprings. That means first 4 parents plus these 4 offsprings. Now if we add, if we close, if we combine, we will get 8 solutions. Now obviously this set of 8 solution average fitness value will be much more higher than the earlier set of 8 solution what we got in the initial population. Check it here. Initial, obviously this see no negatives. That means all these things are increasing only fitness values. Okay, now let me check which is our best solution here. Since it is single objective optimization problem, obviously we will get one solution as a result. So which is our best fitness value here? Check what you are doing. NumPy.max, obviously it will find out the max value. NumPy.sum, see what it will do. It will find out the fitness value only now. NumPy.sum, new population into equation inputs, what it will do. New population into equation inputs. That means it will multiply the values, weight values with the input values, weight values with the input values, and it will do it row wise It will sum all these values and it will give the fitness values for each and every solution. So once I am writing this statement numpy.sum, here it will give you 8 values. Among these 8 values, which one is maximum? For that purpose, I need to write numpy.max. Now, are you getting the fact? How we are coming to that point actually? So see here, whatever you are finding, best result is this one, 61 point something. Check here, what is the best one? Obviously, if you go through, best one will be this, 61 point this. So this is your best. This is your best. So now in this best solution, what you need to find out? We need to find out what are the various values. Okay, what are the various weight values in the best solution? How to find it out? Best solution, best fitness value we got. We need to find out the various weight values in that best solution. So for that purpose, we need to write it that firstly see what we are doing. So since here we are writing, so best match index. So it will give the index where fitness value is maximum. See. Best match index equal to numpy dot where fitness is equal to max, numpy dot max fitness. So right now who are not that much comfortable, don't know this Python programming, this kind of code maybe a little bit look odd for you. But again, believe it, these are very simple coding. So once you will understand little bit Python, then you will find writing this kind of coding probably much more important. Once you will once you will learn Python, probably you will, I think you will not be in a position, you will not be agree to write C++ programming because that is too much difficult. Right? Python is very, very easy. See how so much complex logics we are writing only one statement and so much complex logic we are solving. So it is giving the maximum, the index where fitness was maximum. If you write using C programming, if, else, then many things you need to write for loop anyway. So we are getting the index, best index where the fitness value was maximum. Now, from that index, we need to fetch the various weight values. So how we will fetch the various weight values from the index? So this is the this is the case. New population best match index this. So it will give you the various weight values which are there in this best match index position. Okay, what are the various various weight values are there that will give you. Now let us check 61. For 61, what was the position? For 61, last one. Okay, 61, it is the last one. That means this one. So these are the various weight values for this maximum fitness value 61. So we are trying to recover these values because 61 is not important for us. Values are important for us. These values we are trying to find out. Okay. So now see. So that purpose we need to write this thing and it will give you these values. So this is our final solution. Now see here. See interestingly how so fitness value is how increasing. It is 61 point something. So I have done only one iteration. And in that manner, you need to move through multiple number of iterations. As morning sessions we are telling or someone was telling that in each and every iteration, we'll find out average fitness values. And in some successive iterations or consecutive iterations, if we find the average fitness value is not that much changing, perhaps we'll close there. We'll terminate. So we have done only one iteration. Again, we are increasing, finding that much improvement. Now you can imagine if you go for several number of iterations, how the fitness value will be improved. See, this is a fact that see here, automatically you will find out that more positive numbers will be coming from with the positive inputs and less negative values will be coming with the negative inputs. Okay, so that to maximize our function output. So what I told so far, this is the simplest genetic algorithm, but I believe that you have got some ideas that how to execute, how to write a program using Python programming to solve some problem for genetic algorithm. So next we will move to multi-objective optimization. And in the next 1.5 hours, so we'll try to understand this multi-objective optimization. Okay. So now let me check. Okay. So we are coming through multi-objective optimization. So in multi-objective optimization, whatever we have done here, so see, we have considered a data set. Just check it very clearly. So you need to pay your proper attention if you want to understand this MOGA, multi-objective genetic algorithm programming. Because writing a program using simple genetic algorithm is not that much difficult. But once you are writing something for this multi-objective optimization, this is really a difficult programming. So now you will see, you have seen the programming with single objective optimization. If you see the program, whatever we have written for multi-objective optimization, perhaps you will find out the depth of the programming. See, so whatever we have written. So this is a data set. So this is an, I should say, synthetic data set. You know, synthetic data set means this is user-defined data set. This data set only we have defined for the sake of simplicity of this programming. Very simple data set we have selected. Just check. So some tasks are there as well as some virtual machines are there. Once I am writing T1, T2, T3, T4, these are some set of tasks. Okay, and V1, VM1, VM2, VM3, VM4. So these are some set of virtual machines. So how many tasks are here in this example? 30 number of tasks are there. How many virtual machines are there in this example? 10 number of virtual machines is there. Okay. So this is one data set. This data set we are considering for the cost purpose. That means I mean to say, if you execute task 1 T1 on virtual machine 1, this will be your cost. Whatever right now I am highlighting. If you execute task 1 on virtual machine 2, this will be your cost. Task 1 virtual machine 3, this will be your cost. Similarly others. Are you getting? So this is one matrix in terms of task 1 to 30, 30 number of tasks, 10 number of virtual machines. In terms of cost, we have done it. Okay. What is your objective in terms of cost? So obviously, we want to apply the task into the virtual machines in such a manner, cost will be minimum. Okay. Next, another matrix we have taken here. This is your reliability matrix. Okay, but number of tasks are same. Number of tasks is 30. What is number of virtual machine? Again, it is same, that is 10. So again, so if we apply task 1 to virtual machine 1, this will be our reliability. If we apply task 1 to virtual machine 2, this will be our reliability. Similarly, for task 1 on virtual machine 3, this will be our reliability. Similarly, others. So once we are working with the reliability, what should be your objective? Obviously, our objective should be to maximize the reliability. Now see here. We want to minimize the cost and we want to maximize the reliability. So right now, actually now we are working or we are having two objectives. We are having two objectives. So first objective is to minimize the cost wherever. Second objective is to maximize the reliability. So this is a perfect example of this multi-objective optimization problem. So here we are working with this by objective. So try to understand this objective once again. So cost we are another one objective, reliability is our another objective. Cost is first, reliability is our second objective. Okay. We have considered 30 number of tasks and 10 virtual machines. What is our assumption here? What we want to do, our objective? So our goal is to apply this task on these virtual machines so that cost will be minimum, reliability will be maximum. Now let me check. So from this matrix, these two matrix, can anyone tell what will be the size of our solution? What will be the size of our candidate solution? Now see here. We have 30 number of tasks. On this 30 number of tasks, we want to apply on this 10 virtual machine. Obviously, size of our solution will be 30 only. Because those 30 tasks we want to apply on the virtual machines. Okay, ultimately our objective is to minimize the cost and to maximize the reliability. So let me now come to the program. It is a very high density program. Just you should have your proper attention to understand. If you miss something, the remaining parts simply will be missing for you. Now see. So this import pandas as PD, as I was telling, pandas and numpy. So these two are very important libraries in Python programming. Pandas normally we will use for this data frame, data related operations, and numpy normally we will use for this number related operations. Okay, time copy we have selected. Okay, next check. Here I have written something from Google Colab. See, from Google Colab, import drive content this. Why I am written that? Because here the data set whatever we have considered, this data set I have kept on my Google Drive. Okay, data set I have kept on my Google Drive. So here I want to access the data set from my Google Drive. For that purpose only this statement you need to write. Now this thing will come. See, it will ask permission actually to mount that data set from your Google Drive. I have given access. Now see, now that means Google Colab can access my drive, okay, to take care of this data set. Okay, that access I have given to this Google Colab. So are you getting the meaning of this statement? Once we keep our data set in the Google Drive, then this statement you need to write to mount our data set from the Google Drive. Okay, next. See, so next whatever we are trying to do, just check. So from the Google Drive, we want to fetch the data set, we want to keep our own variable. Okay, so this is task VMS cost, task mean task, VM mean virtual machine. So task VM cost, so here what are doing? PD.read Excel. What is PD.read Excel? PD means pandas. Read Excel is a method. So PD.read Excel, that means it will read the Excel file from your drive, from your Google Drive, what you have mounted using the earlier command. See, VMS cost, PD read Excel, it will read the Excel file, where the Excel file is there in this location, in this name. Sheet name equal to cost, because in your Excel file, as we have seen, two sheet is there. One is the sheet cost, second one is the sheet reliability. So here it is sheet cost, index column equal to 0. That means, so it will read the content of the cost data set and it will keep in this particular variable, task virtual machine cost. Okay. Now, next, task virtual machine reliability equal to pd.read Excel, again same thing. It will read the Excel file which is there in this drive, and in this name it will read the sheet name reliability. So it will access the sheet reliability from that Excel file. Okay, and it will write the content into task VMS reliability. Let's see. Next, see here. So now check. So one shall simply write task VMS cost. See, nothing, no need to write printf, no need to write cout, no need to write system.out.println like a Java, C++. So simply we have written that line, all things are coming into picture. See. So this is the data set that was in Google Drive. From Google Drive we mounted, we kept in our Google Colab environment. Okay, under this task VMS cost variable. Okay. So similarly, if you execute this right, task VMS reliability C, this is our reliability data set where 30 tasks is there as well as 10 virtual machines are there. So this data set we mounted, we fetch it from our Google Drive and we are storing in our Google Colab using this variable task VM reliability. Next, what we will do next? That means now we have we have got access of the data set and we have fetched the data set from Google Colab or our simply or our Google Drive into our Google Colab environment, so that we can do some manipulation or do some work on those data set. Next, initial setting. So what is your number of tasks here? Number of tasks is 30.
So
Okay.
am I audible?
Yes, please tell me.
Sir, sorry to interrupt. Sir,
Oh, no problem.
actually, I want to know, so what is the purpose that we are going to do this Python programming things. We are going on continuing this Python programming. What is the purpose, sir? What we are going
Yeah,
to
since
find
no,
out,
what,
sir?
yeah, actually, since this is an entirely hands-on session, first session I told the theoretical ideas behind it. Since this is a hands-on session, so it is supposed that we will implement it. We'll solve some problem using some programming. As you know, once we want to solve some problem, there is no way you need to apply some programming to solve the problem.
Yes,
So that's
yes, sir.
why we thought that we'll discuss this Python programming to solve these two problems. Okay.
Sir, the data set you are using, is it possible to share for us to practice in later and future
Yeah,
reference
once
purpose
once
also?
we'll yes, yes, yes. Once we'll complete the session, so definitely I will, if you request, obviously we'll share. So I think you can
Yes.
note down my contact number. Do you have my contact number?
No, sir, I do not have, sir.
Oh, okay. I think in the first session I have given it. Write down 8536 8
So 8536
8536 00
00
9758.
9758.
This is as
Thank
well
you,
as my
sir.
WhatsApp number. So once the
Yes, sir.
session will be over, please drop me a message that you are the participants or some from this workshop, and then
Yes, sir.
please then I can share you. Okay,
So
at the
actually,
earliest.
it's very rare session, sir. I'm actually attending from the state of Assam.
Oh, okay,
Because
okay.
I'm very much interested. So, if possible, please, through this platform and session, I request organizers, sirs, and respected sirs and ma'am and members to please share the PDF material and video record also, sir. Please, through this message.
Actually, you
Thank you,
see,
sir.
since this is ENICT, then this is I think being done with ENICT Academy. This IIT Roorkee. So normally
Yes,
we have in NIT Warangal also an ICT Academy, but ENICT Academy normally taking the copyright of all video materials. I don't know. I feel that video recording is not possible to share with any of the participants. Copyright is entirely going with ENICT Academy. So you know ENICT Academy that is sponsored by I think that Ministry of Information Technology, Government of India.
Government of
So
India.
yeah. So since this all these things are being sponsored by Government of India, ENICT Academy don't have the authority to share these video recordings. Only they can share the study
But, sir,
materials. Yeah.
yes, so I just want to add few lines.
Hmm.
Like, sir, we were told that the video recordings will be just shared, not downloadable format, but that can be shared after the
Anyway,
end of.
so anyway, the organizing committee that may be doing that. What I am telling that from the ENICT Academy, because in NIT Warangal we have also ENICT Academy. So it is a clear
Yes.
instruction from ENICT Academy that whatever the video recordings you are having, copyright is entirely going for this ministry. So if you want to share, obviously you need to take permission from ENICT Academy. If they permit, if they allow, only then you can share. Otherwise, you cannot share. Okay, anyway,
Yes.
so I think maybe
Thank
your
you.
organizing committee will take permission from ENICT Academy and they will share it. I have no objection from my side
Yes.
because the copyright is going entirely to ENICT Academy, IIT Roorkee.
Yes.
Okay,
Thank you, sir.
so yeah,
Nice
thank you.
talking to you, sir.
Thank you.
Thank you.
So what I told, yes. So this is the initialization settings. So whatever we are working with here. Actually, since this, explaining this programming in any of the session is quite difficult actually, because it need proper attention, proper concentration to describe the programming, and participant will understand only if they know Python programming. Otherwise, maybe they will understand the concept, but in-depth understanding may not be there. Okay, that first session I was telling that Python programming, we need to learn to understand this kind of solution. Otherwise, sometimes we might feel it very difficult to understand. But since it is a hands-on session, so as per request from the organizers, I am coming up with this Python program. Okay, so this is the initialization settings. So here number of tasks equal to 10, then number of virtual machine equal to 30, as you have seen already in the program. And here this population size equal to 50. Now here we have considered population size as 50. Now see. On the earlier genetic algorithm, we considered that population size was, I think, 8. Here we are considering population size is 50. Number of iterations we are considering 500. Crossover rate 0.8, mutation rate 0.2. So if you have attended the morning session, you can check there I itself told that crossover probability, it should be from 0.6 to 0.8 and mutation rate maybe from 0.2 to 0.3. So here mutation selection rate, another variable we are considering 0.4. Now what is the applicability of this mutation rate? Obviously we'll discuss at right time. Now let us see here whatever you are doing. Just check it here whatever I am trying to do here. See here for speed up our process, what you want to do initially in that variable that task virtual machine cost, okay, in that data frame. So we had the entire matrix task virtual machine reliability. In that data we had the entire matrix, but here what you want to do from the matrix we want to convert it into list. So if you are well aware about this Python programming, then you may be knowing that if you can do that, then we can do necessary computation very much easily. So that is our task here. So task VM cost, see, whatever the data set we got earlier, here using this statement, the entire data set I am trying to convert into list. Okay, that's why I am writing list map float task virtual machine this ith location I for I equal to I in range number of tasks. What is number of tasks? Number of tasks is 30. So for each and every task, okay, so what are the various costs associated with it, with the virtual machines? Okay, that I am making, I am converting into floating point number as well as all these values I am storing as a list in this variable. So simply that statement I am writing as from this matrix I am converted into values, floating point numbers, and ultimately I have stored in this variable task VM cost. And similar thing I am doing for this task virtual machine reliability. From the matrix, I want to convert it into list and I am storing here. Now see, this is list. See, this is the list map float virtual machine reliability. Location this for I in range number of tasks. That means I equal to 0 to 29. As you know, for loop always start with index value 0. So I equal to 29. What are the various values, various reliability values for task 0, task 1, task 2? All values I am converting into floating point number and making into list and putting in this variable task virtual machine reliability. Okay, now let's see how the values will look like. Now see, this is a list only, just check it carefully. This is not showing in terms of matrix. Okay, this is not showing in terms of matrix. This is list values only. Just check how many values are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these 10 values belongs to first row, okay, of our cost matrix. It is the first row only. Next, second 10 values. It will belongs to the second row, okay, of our cost matrix. So like that, here we will find out this, it will covering all this, I think 30 number of task values actually. Okay. So next, now check how these values are coming. Virtual machine task reliability. Again, the same thing. Here we will get, just check first 10 values are there. Okay, these 10 values is coming from task 1. Remaining 10 values will come from task 2, right? 30 number of task values are there. Here these values I am showing in terms of list. See how many values are there, or because 30 number of task values I am storing here. Okay, so nothing else from the data frame we are converted into list here for the sake of simplicity of our computation. Start time, okay, we have taking into account start time. Okay, next we will start from the, so initialization is done. Okay, once initialization is done, next we will start from this part or main programming. Okay, this is the starting version of our NSJ2. Okay, initialization already done. See here, whatever I am writing, base list, based object, all these are making empty. So these variables I am taking, maybe I will be using this variable later on where I am making all these things as empty one. This population list, okay, population list is empty. These are the empty array only I am creating. Okay. Next, for I in range population size. What is our population size? Population size is 50 only. You can remember. Population size is 50 only. This is the for loop syntax. What I am doing? This in this random number. So see what I am doing. Just check it very clearly. List numpy dot random dot permutation task. Number of tasks. What is number of tasks? Number of tasks is 30. Okay, so I am generating a permutation of those 30 tasks randomly for that purpose and putting them in a list. So for that purpose, you need to write this statement. So generate a random permutation of those 30 tasks. Okay, and then put in a list, and then values you need to store here. You may ask why you are doing that. As I told actually that in your initial population, what will be there? Initial population, actually some set of solutions will be there. As I told you can remember. So here, what is our solution size? Each and every solution size is 30 only. You know, we have 30 tasks. What was our target? Our target was to assign those 30 tasks, okay, in virtual machine so that cost will be minimum and reliability will be maximum. So initially we considered 30 random number of tasks. Okay. You see that in the table, task was given from task 1, task 2, task 3, task 30. But here what we are doing, we are generating some random permutations of those 30 number of tasks, putting them in these variables, and then population list dot append this random dot number. What we are doing here? Whatever the random number of tasks we have generated, that task we are adding in the population list. Append with the command for that. Are you getting the fact? Now check. What is population list? You see initially what I did. This population list is empty. Initially I made it. Population list is empty. So that I can add whatever I am getting in my population list. Now the things will come. Just check what I am doing. For I in range number of tasks. Here what I am doing, check it carefully. Population list ij equal to population list ij modular division of this number of virtual machines. It may be surprising. Why I am doing that? Already I have generated 30 random number of tasks. What is the need to do that? Now see. What I told, ultimately as a solution, you need to find out which task we have assigned to which machine. We have a sequence of tasks, which task we have assigned to which machine. So as a result, what will come? Task will come or machine will come. As a result, we will get the machine only. That means, see, so once we are doing modular division, number of virtual machine, so it will give you the number from 0 to this 0 to 9 only, because you are having 10 virtual machine. So what will be our ultimate solution? In that solution, we will get the numbers from 0 to 9 only. Are you getting the fact? We told that our objective is to assign the task to the virtual machine. We have 30 number of tasks. 30 number of tasks we need to assign the virtual machines. How many virtual machines? 10 virtual machines. That means as a result, you will get the number of virtual machine. Okay, this is for task 1 assigned to virtual machine 1, task 2 virtual machine 3, task 4 virtual machine 1, task 5 virtual machine 3. So this 1, 3, 5, 3, 9, these are the result actually. This should be our final solution. Final solution will give you, it will resemble the virtual machines only. It will not give you any task. Final solution, it will give you the virtual machine sequence where you can apply your task to those sequence of virtual machines so that cost will be minimum and your reliability will be maximum.
So
yes, please tell.
So in that case, for this kind of a different task, we have to store the data individually in different machines to to populate this kind of results, sir? Or the data set has to be stored in one particular machine, or what is like this, sir? I'm in a doubt, sir.
See. So this problem is not that much complex. This is very simple. So virtual machines, yes. So whatever I am telling, that ultimately that task we need to assign to the virtual machine. Now,
Yes, sir.
the task we need to apply to the virtual machine so that all these objectives will be satisfied. Now here
Sure.
problem is that, what is our main problem here? Main problem is that which task will be assigned to which machines.
Yes, sir.
So that we'll get the optimized output here. Okay, that's why I was telling that in that manner you need to assign the task to the virtual machine, and as a result we will get only the virtual machines. As a result, we will get any task. What the result it will
Yes.
show? Some sequence of virtual machines. It will show 30 numbers where all numbers will belong to 0 to 9. That means task 1 will be assigned to that machine. Task 2
Yes.
assigned to that machine.
That machine.
Okay. So
Thank you,
now,
sir.
yeah, okay, thank you. So now that was the concept. Now here, see what you are doing. For n in range number of iteration, what is the number of iterations you want to consider here? So number of iteration is 500 that you want to consider here. Okay, next see what you are doing. Parent list copy dot deep copy parent population list. This is very interesting. Here I am using deep copy. You know, some difference is there, deep copy and shallow copy. Why we are using deep copy here? What it will do? Whatever the population list, see here, you are getting some population list. Okay, so that population list you should copy in your parent list. In your C, initially what we made, this parent list. So whatever is our initial, I think parent list we made empty in very fast. So whatever population list right now I am getting this 50 items, that 50 items I want to add in parent list. How to do that? For that purpose, you need to write this for parent list equal to copy dot deep copy population list. Deep copy means what? What is the difference between copy and simply deep copy? You know, deep copy, if we apply deep copy, so that means some set of solution will be copied to another set of solution. And if you do some changes in the destination, that changes will not be reflected in the source. If you don't apply deep copy, you copied from source to destination. If you do some changes in the destination, the changes will be reflected in the source itself. So that is the difference between deep copy and shallow copy in the context of this Python programming. Offspring list. Okay, initially we made offspring list equal to empty. Now see, whatever we are trying to do, check carefully. We are implementing crossover here. For M in range, population size by 2. Obviously, it is 0 to 25. Our population size is 50. We are making it in 2 half. Next, see. Parent 1, population list 2M. See, that means parent 1. Whatever we are selecting as parent 1, see, initially what is the value of M? Value of M is 0. What is 2 into M? 2 into M means 0. So list, population list S0. Just check it. What is S? So here I told you now that population list, whatever we are getting the solution. So whatever you will get here, just check. Population list this 0. That means population list 0, population 0, first solution will be considered. And what does it mean? This colon. I am writing simply colon. No left side, nothing right side. That means what is there? Okay, what is there in the first chromosome? All things will be coming to parent 1. Very much interesting that simply colon. Whatever there in the first chromosome, automatically all values will come to parent 1. So how many values will come to parent 1? 30 values will come to parent 1. Okay, from first chromosome. Now see. If M equal to 0, then what is 2M plus 1? 2M plus 1 equal to 1. So if 0 we say be the first solution, 1 we say be the second solution, then from the second solution, what are the various chromosome values? Those values will be coming to parent 2. Are you getting? That means now parent 1 be our first chromosome, parent 2 be our second chromosome. What we want to do? We want to apply crossover on this parent 1 and parent 2. Now see what I am doing here. Child 1 equal to parent 1, this colon again I am writing. That means from parent 1, what are the various chromosome? Chromosome means gene values only. So what are the various values? 30 values was there in parent 1, that will be copied to child 1. What are the various 30 values are there in parent 2? That will be copied in child 2. Okay, so simply parent 1 values we copied to child 1, parent 2 values we copied in child 2. Next, what you are doing? Just see. Writing cut point equal to list numpy dot random choice this. What does it mean? Numpy dot random choice number of tasks to this. See the statement. So that means from number of tasks, what is the value? 30. From 30 values, it will consider 2 random values where there will be no repetition. That means from 30 values, it will select 2 values without any repetition. Okay, so those two are cut point. Maybe 5 and 7 will be selected. Maybe 9 and 11 be selected. Maybe 13 and 10 be selected. Then what you need to do? Then we are writing cut point dot sort. Whatever 2 values you have selected earlier, those 2 values you are applying under sorting. That means it will be ascending order. Maybe 2, 3 selected, maybe 9, 10 selected, maybe 11, 19 may be selected, maybe 1, 10 may be selected. Okay, 2 values you are selecting without repetition. All those 2 values you are keeping under sorting. Next, the interesting thing, just take it. Child 1, see, cut point 0 to cut point 1. Let us assume cut point 0 is 5, cut point 1 is 9. Here it is giving actually cut point 0 is 13, cut point 0 is 13, cut point 1 is 18. So in child 1, from 13 to 18, those values you will take from parent 2 from exactly 13 to 18 position. Very much complex logic to understand. That's why I told it's multi-objective optimization is really difficult. See here. Cut point 0 to cut point 1 in child 1, those values will copy from parent 2. Cut point 0 and cut point 1 in child 2, those values we are copying from parent 1. Now see the situation. How we are implementing this information exchange, that part, and how we are implementing the crossover here. Okay. So that means now what we did, 0, 1, these two parents selected, we implemented the crossover. Then parent 1, parent 2 may be selected, we will implement the crossover. Parent 2, parent 3 may be selected, we will implement the crossover. Like that, here we are implementing the crossover. Next, offspring list dot extend child 1, child 2. In the offspring list, we are adding this child 1 and child 2. Whatever right now we are getting. See, initially offspring list we kept as empty. So right now we got 2 child solutions. We are adding those 2 child solutions in our offspring list. Okay, so now crossover is over. See how difficult with the crossover actually. So 0, 1, 1, 2. Next check. If m be 2, then what will happen? 2 into 2, 4. This is 5. So 4 and 5 will be selected for crossover. If m equal to 24, that means 24 into 2, 24 be 2 into 2, 48, and then 48 plus 1, 49. So 48 and 49 will, that two index solution will be taking part in the crossover. Okay, so that means from a set of 50 solutions, ultimately once we have completed the crossover, we will get exactly the set of 50 solutions, wherever our each chromosome size is 30. Okay, next mutation. Take it. How we are applying mutation here? Just see here. So M in range offspring list, what you are doing? So in offspring list, how many solutions are there? In offspring list, obviously 50 number of solutions are there. Now, mutation probability numpy dot random dot rand, what it will do? Just check. That's why you need now this fast, whatever we discussed earlier. NumPy.rand. Here I have defined, yes. What is mutation rate? Mutation rate, we are telling it is 0.4. What is number of mutation jobs? See, round number of tasks into mutation selection rate. If mutation selection rate is 0.4, your number of tasks is 30, so that will give 12. That means here I mean to say that number mutation jobs in that variable, the value 12 will be stored. Okay, so 12 is getting stored there. Now let us see what we are doing with this value 12. Now see here. So mutation probability numpy.random.rand, that means you are getting some value as mutation probability. Okay. Now whatever you are getting, if mutation rate is less than the mutation probability, what we thought as mutation probability? Let us check which value we consider as mutation probability. What was the value for mutation probability? Mutation rate is 2 only, 0.2. Just take it. What I was that? What was that? Yes. So see. So here we have generated some number as mutation probability. Now, if our mutation rate, which is 0.2, is less than the mutation probability, only then you will go for mutation. Otherwise, no. Now see the situation actually. So that's why I told that no. So again, which solution will keep under mutation, that is also random. Okay, sometimes how many solutions will keep, that also will come randomly. So everything will be randomly only, no biasness, because all this multi-objective, single objective optimization, whatever you are using, all are stochastic in nature. Randomness will be an inherent part of all those algorithms. That's why you see each and every point I am applying this random. I am using this random value because I don't want to keep any biased value to any solution. Okay, next see. This mutation change, now see here, whatever doing, m change, numpy.list, numpy.rand.choice, see, number of tasks, number of mutation job, what is number of tasks? 30. What is number of mutation jobs? 12. Replace equal to false. That means from each of the task, okay, each of the task we will randomly select 12 position without repeating of any positions. I think I hope now you are getting. From each and every solution, one solution means it is having some 30 values. Size is 30, 0 to 29. So from each and every solution, we will randomly select 12 positions, because this mutation, this value is 12. We will select 12 positions without repeating the positions. Okay. So those positions we have selected. What we want to do? Actually, those positions only we want to change the value. That is our target here. Now let's see how interestingly we are performing the mutation. Just check it here. What we are doing. See, t value last. Okay. See, in this, what we are doing here. Just check it very closely. What is I? Out of 12, one thing is I here. Whatever the 12 values randomly selected. So that means what are the values in that position, first position, that will be replaced by I plus 1 position? What are the, this is I, here see, for I in range, number of mutation job minus 1, this will be executed from 0 to 11, 12 times. Initially I equal to 0. That means whatever the randomly selected position was I, here I was showing 10. 10 will be replaced by 10 plus 1, 11. Now see the situation, what you are trying to do, just take it very clear, very carefully. Initially we selected 10 random positions for doing mutation. Random position 1 will be replaced by random position 2. Random position 2 will be replaced by random position 3. Last random position will be replaced by the first random positions. And we're getting how we are applying the mutation here. You may ask me, sir, why you are not randomly changing? As you know, in some problem, if you randomly change all these values, you will never get any solution. Like traveling salesman problem. Can you change the cities? Cities will have some name now, 10 cities, 0 to 10. So can you say that, okay, this is my city number 20? You cannot do now. So that means what the what the gene values you have. You need to incorporate the gene values to apply all these mutations. The problem is like that traveling salesman problem, where which are the cities, among those cities only you need to move here there. At the same time, none of the cities
Respected sir, your voice is muted, sir. Your voice is not audible.
yes, now it is unmuted. Okay, thank you.
Yes, yes.
Okay. So maybe this multi-objective optimization is that much complex, system also not allowing you to discuss. Anyway. So next, what you are doing? So crossover mutation, more or less we have performed. Now see. So as you have seen in the morning session, then initially we have with us parent, how many parent solution we got? N number of parent solutions. From n number of parent solution, how many offspring you got? Again, n number of offspring solution. Then that n plus that n, 2n. So 2n, that was the total chromosome. So here, just check. So in the total chromosome, what you will get? Copy the deep copy parent list. That means from parent list, you will get the solution, as well as from the offspring list, you will get the solution. This is your P0, parent list means P0, offspring list means Q0. So P0 plus Q0, that means n plus n, here 50 plus 50. In total chromosome, you will get 100 number of solution. So now, okay, now at least we got the 100 number of solution. What is our objective? From this 100 number of solutions, we need to select best 50 solution. Okay. Now let's see. Chromosome objective record. Okay, we are making it initially empty. M in range, population size into 2 into, so that means M. What is population size? Population size is 50 only now. So 50 into 200 minus 191, 99. So M will be varying from this variable 0 to 99, covering this 100 number of solutions. Now see. So this C generation C equal to 0, this generated R equal to 1. So see, here I mean to say this variable I am using for this cost. This is my cost variable and this is my reliability variable. I want to find out the fitness function right now, fitness value. How I am computing the fitness value, just check it. Cost. Once, that means we are taking the summation of all these costs. Just check. This cost generated equal plus equal to task virtual machine cost this. That means what we are doing for each and every, see, so for each and every task, okay, with which virtual machine it is associated, those costs simply we are adding. Remember it, we are doing it for each and every solution. One solution means what? One chromosome. One chromosome means what? There is some set of, in chromosome 30 number of values are there. All values belongs to some, I think, virtual machine only. Now you need to find out, okay, this task 1 associated with virtual machine 1, what is the cost? Take it. Maybe task 2 associated virtual machine 10, what is the cost? Take it, do the summation. Like that, you need to find out the cost of your objective function. And reliability, once you are finding the reliability, simply you are multiplying all these values. In this manner, we are finding the reliability. So this is your cost and reliability. So, and this is our objective function actually, how we are computing cost, how we are computing reliability. Okay, so this is chromosome. That means here our objective record for each and every chromosome. Here we have taken this. Firstly, we have considered reliability. Secondly, we have considered the cost. Okay. So next, cost. Next. So see, so up to this point, what we got? So we got 100 number of solutions. each and every solutions. We have computed fitness value, and ultimately we kept the fitness value in this matrix. Okay. Next, what you need to proceed? Next, we need to find out the best 50 solutions from the set of 100 solutions. So we need to go for selection. See, we will go for selection process. Okay. So before selection, sorry, we need to go for non-dominated sorting. Why non-dominated sorting is required? As you've seen in the morning, that once we'll apply the non-dominated sorting, so it will give us some fronts. Right now, I will open, I think, that before discussing none of this, I need to open this PPT. Just check this PPT. Now we are going to implement this non-dominated sorting. Just check. What is the non-dominated sorting, which I discussed in the morning session? Just check. Exactly the same algorithm I will code using Python programming. Just check. So this I told you are getting that, yeah, we got P0, okay, 50 number of solutions. So we got from P0 we got Q0, another 50. Then P0 plus Q0 we are adding R0, now 100. So from here, what you need to do? Now we will apply this fast non-dominated sorting. Okay, we will apply fast non-dominated sorting. Then we apply crowding distance. Okay, let's see. Once we apply fast non-dominated sorting, see this. Once we apply fast non-dominated sorting, it will give us some fronts, where each and every front is a collection of some set of solutions. Now see. I'll come to that algorithm, then I'll show you the implementation. You see, this is the algorithm for this fast non-dominated sorting. See. So what we are doing in this fast non-dominated sorting. Okay, so that I will tell. So let me come through the program. Okay, what we are doing in this non-dominated sorting. Just check. So let me move to this function fast non-dominated sorting. So this is our non-dominated. Where is our non-dominated sorting? Yes, this is our non-dominated sorting. What you are doing? Exactly the same thing we'll do. See. Just check in that particular algorithm. Just check whatever you are doing. Just check. For each P belongs to P population. So this SP means this is the set which is dominated by 1 by P. Initially that will make it null. Number of solutions dominating P, that will make it 0. Now for each Q and P, that means for each Q in the set of solutions, for each solution in the solution set, we'll compare this P and Q. We'll find out dominance. If P dominates Q, then what will happen? Then Q will be added in the domination list of Q. What I said morning in using graphical presentation. Else, if P is not dominated by Q, okay, then what will happen? Then, so if Q dominates P, then domination count of P will be increased by 1. Increased by 1. You can remember what I told in morning. Now, if NP equal to 0, that means domination count equal to 0, put it into fast front. Rank equal to 1. Make the rank equal to 1. Put it in fast front. F1 equal to F1 union P. That solution you are putting in fast front. I equal to 1. Next, while Fi not equal to null, that means if the fast front element are not equal to null, then each and every element from fast front do the same thing. See, Fi not equal to null, Q equal to null. Okay, for each P in Fi, that for each P in the fast front, what you are doing, just check. For each Q in SP, what is SP? Just check. Other solutions. See, or let me make it clear. Oh, how it is not making it clear. Should make it. Okay, that options is not coming. Okay, no problem. Okay, no problem. Now see what you are doing. For each P belong to front. For each P belongs to my front I, fast front, what I am doing. For each Q belongs to SP, that means whatever the elements are dominated by my fast front element. Are you getting? what is SP? Dominated by P. So dominated by Q. So what are the elements that is dominated by Q? What is Q? Q are the elements which are in my first front. So once those elements are dominated by Q, their counter will be reduced by 1. So let us see here. Just check. Check here. I am considering here this element, this. So this number 1. So 1 dominates all these elements. That means their domination counter will be reduced by 1. So exactly the same thing I mean to say here using this algorithm. Okay. In case now NQ equal to 0, that means if NQ equal to 0, for some cases we are getting it is 0. So put them in the second front. Now see. So we are keeping them in the second front. Rank, Q rank I plus 1 and putting in the second front and so on. We are continuing. Now exactly the same thing I will try to explain using this Python programming. Now see here. So now you are getting what is S, N, all these things, front rank, all making it null. So P in range, population size into 2. Population size is 50, 50 into 2 means 100, since we are now considering with this 100 number of solutions. Next. SP equal to null. Solution dominated by P are null initially, empty. NP equal to 0. Solution dominates P, also 0. Now the fact, see here. For each Q in range this, that means we are considering solution P and solution Q. Let us assume P be our first solution, and Q be our second solution. Okay. Two solutions we are considering now, P and Q. This is for loop, nested for loop, P and Q. Let us assume P be our first solution, Q be our second solution. Then what you are doing? Just check. Chromosome objective function record P0. What does it mean? 0 means it is the reliability. P, our solution P, Pth solution, 0 with the reliability. Qth solution, 0 with the reliability. Pth solution, 1 with the cost. Qth solution, 1 with the cost. Okay. So if for the Pth solution, reliability is more than the Kth solution. For the Pth solution, cost is less than the Qth solution. Good. Reliability is more, cost is less. Or if reliability is greater than the Qth solution and cost is less than the Qth solution, it is also good. Okay, next. If reliability of the Pth solution is more than the reliability of the Qth solution, but the cost is less than equal to the Qth solution, are you getting? When one solution will dominate the second. If at least for one objective, it performs better than the second solution. And for all other objectives, at least it should not perform poor than the second solution. Now see how those things you are writing using this Python programming. So if this is the case, then what will happen? That means specifically I can tell if this is the case, dominates Q. Okay, obviously if Q is not in SP, then SP dot append Q. That means here in the list, domination list of P, we are adding Q. Now see the situation here. And this is if, and you know this is else if. Okay, else if, that means if Q dominates P, then what will happen? Then domination counter for P will be incrementing. See, here what is happening? In the else case, Q is dominating P. That means NP equal to NP plus 1. Initially NP was 0. Now it is becoming 1. Domination counter for the Pth solution, we are incrementing to 1. So from this, my graphical presentation, you can check it. Now from this is my graphical, okay. Yeah, from my graphical presentation, you can check it. Now see here. Just check it. So for this, domination counter was 0. Okay, let me, yeah. For the solution 3, domination counter was 3. This is my solution 3. because these three solution dominates this. So what is 1 plus 2 plus 3? So that's why you written N3 equal to 3. Okay. I hope that up to this part you are getting. Now see the interesting fact. If NP equal to 0, that means if domination count for some solution is 0, then obviously those are rank 0 solution. That means first rank. If P is not in front 0 dot append P. That means for which solution we get this as 0, simply we are adding to that solution first front. We are adding to those solution to first front. I equal to 0. Now see, while front I not equal to null, that means some element is there in the first front. QBMT take. For P in front I, that means for each and every element in the first front. For Q in SP, that means for each and every element in the for one element in the first front, if P is there in the first front, and if SP is dominated by Q, what is SP? SP be the set of elements which is dominated by Q. Sorry. For each and every element in the first front, for P in front I, if Q is in SP, that means if Q be the list which is dominated by P. For each and every element in front I, we need to check which element it is dominating, and for those elements, that domination counter should be reduced by 1. So for Q in SP, just check it very clearly. That means Q is there in the domination set of P. Obviously, then you need to decrement that domination counter by 1. Similarly, after doing that, if we have found NQ becomes 0, then the rank of the Qth element you need to increase to 1. That means that will become to the second front. That will move to the second front. If Q is not in Q, Q dot append Q. That means that will move to the second front. Now, are you getting exactly the same thing how we are doing using this Python programming? That is the code for this non-dominated sorting, whatever we have implemented using this Python programming. Okay, now next we will move fast. So our crowding distance, this non-dominated sorting is over. Okay, so once non-dominated sorting is over, then what we will get? So we'll get the set of fronts. Okay, return front. What it is returning? It is returning the set of fronts where each and every front consists of some set of solutions. Okay. Where we actually here, where we are crowding distance here. So now this step is over. So once this step is over, we will move to the next step, this population list here. Why you need to do that? See here. So right now our front selection is over. That means we are getting 2n number of elements as a summation of all those front elements. From those 2n, we need to select first best n. How we need to do that? For that purpose, here I am writing selection. Okay, let us move to the selection page. Selection method. Where is our selection method? So let me check. Where is my selection method? So this is my selection method. Okay. This is my selection method. So what I am doing here, just check it very clearly. So before selection, let me come to the PPT. So what you are doing during selection? Just check. Yes. So here in this case, what we did, so see. Take it here. What we did? So our non-dominated sorting is over. That means we are getting all front elements. Okay. From these front elements, we need to do the selection and apply crowding distance mechanism to select best 10 elements. So this is our set of 2n. From this 2n, we need to get n number of elements. So that means we need to select, okay, which elements we will select from those fronts. For that purpose, we are applying this selection. That means here, front 1 directly you can put, as I mentioned in my morning session, front 2 directly you can put, as we consider front 1 element supposed to be better than front 2, front 2 element supposed to be better than front 3, and so on. Front 1, front 2 you are keeping, no problem. Once you are keeping front 3, problem, because front 3 size is more than this amount, this remaining space. Then in front 3, the solutions inside the front 3, we need to apply crowding distance mechanism, by which we will get the best remaining solution which we can fit here to make the size adjust to n, and remaining elements simply will discard. Okay, let me come to that part. See here. Okay, so n equal to 0, new population equal to empty, while n less than population size. Very good. What is our population size? Is 50 only. N, what is the value of n? Initially 0, because one by one we will add the solutions from the fronts. Okay, next. For I in range front I, length, how many front you have? Here this length front, it will give you how many fronts you are having. Okay, maybe it is having 7 front, that's why the value is coming 7. Next, n equal to n plus length of front I. What is I? I is 0 only. What we are initially doing? With n, we are adding, what is n? N initially 0. We are adding the elements from the front I. What is front I? Front I is here front 0. So initially we are adding front 0 to our set of solutions. Okay. And if we find that by adding the front 0 elements to our set of solutions, size is becoming more, it is greater than n. Let us assume front 0 elements we are adding and we are finding size is more than that, more than 50. Then what you will do? If n is greater than population size, after adding the front 1 element to this n variable, if we find size is exceeding n, then what you will do? Size is exceeding, not n, size is exceeding the population size 50, then what you will do? Then we need to go for this crowding distance. Compute crowding distance. Okay, that means in a particular front, what are the various solutions are there? We need to check which solution, for which solution crowding distance is more. Only those solutions we should keep, and the remaining solution we need to discard. Let me check where is my crowding distance. Okay, so again, different case, let me assume that by adding the first front element, the size is not exceeding 50. See, first front elements I have added to the variable n, and I am finding population it is not exceeding 50. Then what I should do? Then directly you can add first front element to n. See what you are doing. Then else new population extend front I. Directly front I element, first front element, we are adding to our new population. That I told, that you have seen in the PPT. If no problem, directly add. If any problem, then go for finding the crowding distance. Here we are finding some problem, so here we will go for finding the crowding distance. Okay. This is our calculate crowding distance. Let me check how we can calculate crowding distance. Where is my crowding distance function? Where is my crowding distance function? Let me check. So where is my crowding distance function? Oh, this is my crowding distance function. Calculate crowding distance. So look closely. This is my crowding distance function. Now, how this crowding distance function will work? Before proceeding to this is a very much complex logic. Before proceeding to this, let me show you the theory behind it. Yeah, so that was the logic for doing this crowding this. Exactly whatever the algorithms written here, exactly the same Python implementation we have written there. No changes, exactly similar I did there. Okay, so this is number of solutions. Okay, for each I, we are in set IL distance equal to 0. We are initializing, okay, distance equal to 0. Now, for each objective function, check it. So in our case, right now, two objective function is there. One is cost, second one is reliability. Very good. So for each objective M, we need to sort it. As in the numerical example, what I have showed in morning session, you may remember it. for each objective function, we need to sort the set of solutions. Okay, let me sort. I have sorted it. Let us assume. For cost, I have sorted. For reliability, also I have sorted. Then this first distance and last distance, we are considering infinity. You can remember, I told two extreme solutions, we will consider their crowding distance is infinity, because you don't know which is their next nearby solution. One nearby solutions we know, but what is the next, that side, that you don't know. That's why we consider that is infinity. Now the most important thing will come. See, for I, just check it here. For I equal to 2 to L minus 1. Why 2 to L minus 1? Because these two solutions already we have ignored. Now see, I distance, initially it was 0. I distance this. See what we are doing. If we are finding the crowding distance for this ith solution, that means previous and next we need to consider. If I plus 1 be the next, I minus 1 be the previous, this next and previous we need to consider. What is m? So m be the objective function. You know, so for one objective, for all of the objective functions, you need to repeat the same thing. This is the previous one, maybe this is the next one, this is the previous one, okay, and here dot m. What dot m? M be your objective function. What was the value of previous solution which correspond to this objective function cost? What is the value of the next solution which correspond to the objective function cost? Right, that you need to do. And this is maximum minus minimum. That means what was the maximum objective function value for cost for all the solutions? What was the minimum objective function for cost for all the solutions? That you need to do here. Now, if we look closely our example, so I think morning I told this example, you can remember that here we have used two objective, one is time, second one is cost, and here we have given which is maximum minimum values. So I'll not repeat it since morning already we have discussed it. Okay, now let me come to my program. See here. See, so what we are doing. So see, here very important thing what we are doing here. See, sorted keys, objective functions, object. That means whatever you are doing here, just check. So we want to sort, actually we want to apply some sorting on this objective function. Just check it for one front. Now see, we are finding the objective, we are finding the solutions which are there in a particular front, we are finding the objective function values, and we are sorting the objective function values here. As you have seen, for each and every objective functions you need to sort their values. Now see, this distance of two extreme solutions we are keeping infinite. Now for range I, just check, in 1 to front minus 1, obviously 1 to, that means 0 and extreme end, 0 and last will be ignored, the remaining things only we are considering. Now see, if local length is 1, okay, else this part you check what you are doing, just see it. Distant sorted keys, because already we have sorted now based on the objective values. So sorted keys, see, distant sorted key is I equal to distant sorted key is I plus, this is important part, objective sorted key I plus 1 minus objective sorted key I minus 1. So this will give you the previous and next solution for this ith solution. What is objective? I mean to say, it will give you the objective function value here. And here it will give you the maximum and minimum values of the objective functions for your solutions. Whatever exactly I shown this, so exactly you will find out that this thing where we have written in terms of Python coding here. Okay, so let us assume that crowding distance already we have computed. So once crowding distance is computed, next what will be our next objective? Let me check where we started actually. Crowding distance, from where we came. Crowding distance. Non-dominated sorting we did. From non-dominated sorting, we are doing selection. Okay. I think from selection only move to the crowding distance. Sorry, your selection. This is your selection, correct. From selection only move to the crowding distance. See. So crowding distance is done. That means now you have the set of solution in your hand, where crowding distance is more, where crowding distance is less. See. If for this particular front, ith front, okay, if by adding the ith front to our existing set of n solutions, it is, if you find that this value is moving beyond to 50, then obviously for that front I, we need to apply this crowding distance. Let us assume on front I, we have applied this crowding distance. What you will get? We will get the ascending order of the solutions. I should say descending order of the solutions. That means you will get the solutions with maximum crowding distance first, solution with minimum crowding distance last, because we know that which solutions having maximum crowding distance, those are the better solution, because we want distance should be more, as our objective is that solution should be diverse, not diverse, well diverse across this Pareto optimal spectrum. Now see here, you are getting the distance. After getting the distance, what you are getting? Just check. We are making it reverse. Check it. So we have done this thing reverse. We got the distance here. What about the distance we got? Initially, we make it sorting. Sort the distance. After sorting means it will do ascending order sorting. Then we are making it in descending order. What is the need of that, as you know? Because we want to get a solution where crowding distance is more to be the first. Solution where crowding distance is less to be the last. I think now you are getting. Then based on that, now see the situation here. So if this is the case, we implemented crowding distance, and if J in sorted CDF, sorted crowding distance, if length of new population is population size, otherwise you add this to append J to new population. That means, see, what is J? J means the solutions which are we have computed based on the crowding distance. So how many solutions based on the crowding distance you will add to the new population? You will add it, you will check, add and check. You are adding and checking. Okay, size is not exceeding 50. Once again add, once again check. Yes, size is not exceeding 50. So that is our crowding distance mechanism. Now if you know Python programming, probably you will get the depth of writing the programming, because this programming is not that much, writing is easier. Huge depth of Python programming is required to write this kind of logic. Okay, so crowding distance is over, selection is over. Okay, selection is over. So once selection is over, whatever you are getting, after selection, we are getting this population list. 50 items we are getting. Okay, that which are the most best 50 items that we are getting from this selection. We have applied non-dominated sorting, as well as we have applied crowding distance mechanism. As a result, we will get first best in number of solutions. Okay, so this population, yeah. So it will return this population list, see, append this total chromosome we have added, and it will return this population list, 50 items, as well as this new populations. Both these things, this selection will return. So selection is over. So next, where we completed selection? Let me check. Where we completed selection, the selection, yeah. So selection is over. That means now, okay, we are getting our population list 50 items. Okay. So next, what you will do? So from this population list, you find what is the objective function for each and every population. As I told, you know, that time I told that once from one solution, one population, you are moving to the, sorry, one generation, you are moving to the next generation. Then for each and every case, for each and every solution, you need to find out the fitness function. Because once you are moving from one solution to the second solution, you know, solution position is getting changed. If you look on the search space, solution position are changing. Once a solution is changing its position, then each and every time you need to find out this fitness value. Because position changing means what? Parameters are getting changed. So once parameters are getting changed, obviously fitness value also will be changing. Now see here. So now check it that what is happening for EC. How many times you need to find out the fitness values? Can you imagine here? How many times once you are implementing multi-objective optimization, multi-objective genetic algorithm, how many times you need to compute this fitness value? It's a very much tedious task. And if your fitness function is complex, now can you imagine how much time it may take to execute this multi-objective optimization solve problem? That's why once remember it, once you are formulating the fitness function, not only for single objective, but for multi-objective optimization, remember it, your formulation for fitness function should be simpler one. Because it will be calling maximum number of time for each and every generation, for each and every iteration, it will be calling. And then if it is difficult, if it is complex, your program time complexity will be unnecessarily very much higher. Okay, so best solution we got. Next, what we did, let me check. Best solution we got it. Yeah, so best solution we are getting here. See, so this is done. This thing entirely we have completed. We are here right now. We are getting PT. 50 solutions we are getting. Again from PT we need to go for QT. From QT again we need to go for PT plus QT. Okay, that we did actually. See here how we are getting PT best, first best n. From this is n. From this n again you will go for this n. Then this is 2n. And again you need to repeat in this loop until unless you will find that you are reaching to the maximum iterations or to that solution where average fitness value is not changing. Okay, let me come to that part. Okay, let me take some water, then we'll come to this part. Almost we are coming to the end. I'll continue for 5 to 10 minutes, then we will take question answer. Okay. So next what you are doing, just check. So as I told that next, so we need to this sheet. We are finding the total list. That means again, we need to find the set of 2n solution means 100 number of solutions. C. Copy, deep copy, population list. Copy, deep copy, base list. Now see the situation. So base list, that means whatever we got, the best solutions. So that solution and our old population, these two things we are adding here. So we will get again a set of 100 solutions. Just check it. From 2n number of solutions, we got n best solution. And before finding the n best solutions, again we had with us first 50 solutions. So we had with us first 50 solutions. From those first 50, again we computed next 50. Then 50 plus 50, we have now 100 solutions. That is here only. Total list, we are having 100 solutions, 2n number of solutions. We are finding the objective function of this 100 number of objective function value for this 100 number of solutions. What we are doing, see, new based front. So on these 100 number of solutions here I have applied, actually here I'm coming to the end. So I have applied non-dominated sorting. That means once we apply the non-dominated setting, as you know, that it will give you the best solution. So that means once I apply non-dominated sorting on this 100 number of solutions, so it will give you firstly some set of fronts. And from the set of fronts, So it will give you some set of fronts where our front one solution will be better than all other solutions. And from front one solution, once I will apply crowding distance, obviously I will get the most desirable solutions. That's why here only I am trying. So this, we are front one, we are doing all these things so for finding the best solution. Now see that whatever you are finding. So here as a result, see whatever was our target, as I told, that multi-objective optimization will never give you one best solution. Instead of that, it will give you some pool of solutions from where, based on the domain expertise, we need to find out what is the best one. But here to show the which is the best actually. But what I am telling, what I am right now I am showing, this is we should not go for that. But for the purpose of making conclusion only I am showing it. So here what I did, from the entire 100 number of solutions we got, we divided it into various front. We considered the first front, and from the first front we applied non-dominated sorting. Obviously we will get one solution as a best solution. Now see, here this solution I am getting as a best solution. Now, can you tell me what are the values given here? What does it mean? See, these values are nothing but the values for those virtual machines. Task 1, apply on virtual machine 5. Task 2, apply on 5. Task 3, apply on 6. Task 4, apply on 6. Task 5, apply on 5. Task 7, like that. Task 1, 2, 3, 4, 5, all 30 tasks. See, here all these values are 30 values. That means you need to apply your sequence of tasks in this sequence of machines so that your this reliability will be this and cost will be this. Okay, this is our final solution. And total time here I have calculated. This is your total time to do that. Okay, now here again I will show you something actually. So some plotting I will show you directly. I'm ignoring all these actually things. So this is our final Pareto optimal front, whatever you are getting actually. Okay, now see, this is reliability, this is cost. So what is our objective? To maximize the reliability, to minimize the cost. So this is our Pareto optimal solutions, whatever you are getting by applying this NSJ2 for our data set. Here I can tell, okay, this solution is little bit diverse only. Okay, this solution because yeah, here I need to apply for 500 number of times, but right now what I did only I executed one iterations only. So obviously you will not get that kind of good solutions here. But more or less what I am trying to show, yes, we are getting a Pareto optimal front. Okay, here few solutions are there where distance is less, and few other solutions are there where crowding distance is more. So with that, so I want to conclude. So here I feel that whatever the programming today, I have tried my best to explain. So maybe you are getting some knowledge from this programming. So I believe that if you are comfortable in Python programming, you will be getting maximum thing from where I am telling. Although the problem complex is a little bit high. But again, if you are beginners in Python programming, I feel that that will give you the inspiration as well as that will help you to understand, okay, if you apply something in Python programming, we can do some complex task much more in simpler manner, in easier manner. Maybe that will give you the motivation to learn Python programming for the purpose of implementing, maybe for single objective optimization or for multi-objective optimization. Now I will close here. So if there is any question, so please feel free to ask me your question.
Now it's time to discussion. Any queries from the participants?
So because this was actually so much lengthy session, so started from 5:50 and almost it is going to 8. So now let us see. Actually, one participant I think asked me few questions. Obviously, those questions are very much, I think I appreciate. That was quite good questions actually. I hope that I have answered these questions, whatever that participant has asked. Also, you know, in morning sessions also I shared my contact number. And here also in chat box now I will share my contact number as well as my email ID, contact number 8536000975. Am I writing correctly? Yes. Oh, 8536009758. Okay, so this is my contact number. I have typed it, just check it, 8536009758. This is as well as my WhatsApp number. And what is my email ID? I will type. Okay, this is my email ID.
Namaste, sir, respected sir and respected ma'am. Namaste, good evening. Actually, just I want to say that these kinds of FDPs are very much beneficial, enriching, and important. And it is an opportunity to be a part of this FDP and the sessions, because these sessions are highly inspiring, motivational, as respected sir Sudhir sir has already mentioned. Because in future also I will try my best to be a part of such kind of FDP. Lastly, I request organizers, respected members and sir and ma'am, please, if possible, please try to arrange, share the PPT slides and of all the sessions and videos if possible, please. Maybe it is like that. Actually, from the starting in middays, I had been told that videos will be shared, but that can only be viewed, not downloadable. That can only be viewed. That option is also okay from my point of view. If is this possible, that would be very helpful for future reference and guide actually. Due to copyright option, we do not need downloadable option. Just viewing option is sufficient, so that you can view actually, sir and ma'am.
Yes.
This is my request, because actually I am attending from the state of Assam and my network connectivity is poor here. Frequently, I sometimes get disconnected, and it happened in many sessions. This happened also. But still, I am trying my best to be continue in all the sessions, and for the future sessions also, I will definitely do the best to be in online. But this is my request. Please look into this. Thank you, sir, and thank you, ma'am. Thank you, sir, for your inspirational and so detailed and elaborated session. Very much. Thank you, sir.
Okay,
Okay, sir, we are definitely
you.
looking into this matter. Thank you for your participation.
Thank you, ma'am.
Okay, so if there is no other questions from the participants, so probably we can close, as we have already shared my contact number, email ID. So please feel free to contact with me, so that we can do some actually fruitful, effective, good collaborative research work. As you know, research work means all about collaborations. So if we don't want to do some collaborations, obviously sometimes research work is going to be very much difficult actually. So we need some collaborations to continue with our research work. At least I feel that some of my participants, maybe they will be collaborating with me, or they will be collaborating with my respected faculty colleagues in Vignan University, so that effectively we can do something. Once again, so I would like to thank my participants. So we listen to me. Yes, please.
Yes.
Sir, please. Sir, actually, myself, sir, Jagat Burman. Sir, I recently enrolled in minor in AI in IIT Ropar, sir. Yes. So I need your suggestion and guidance. What things are basically I have to be in expert, like in AI, ML, DL. Actually, sir, which thing is for career prospect and also for career opportunity is required, sir? That is, I need some suggestions from you, sir.
Okay, so probably that kind of things, I think you can contact me any days, maybe within 6 to 7. So probable time to call me is in any day in evening, 6 to 7. Okay, so that time normally I become free. So please contact me. Obviously, we can discuss in more elaborated manner.
Yes, sir. Thank you for your coordination and support, sir. Thank you, sir.
Okay, thank you.
Thank you, ma'am. Yes.
Yeah.
Nice.
So as I was telling, so once again I want to convey my thanks because morning almost I took 2.5 hours and again 2.5 hours, so that participants may be feeling very much tired. So I won't take that much amount of time. Once again, I want to convey my sincere thanks to all the organizing team members of this FDP or of these international workshops, and obviously I want to convey my sincere thanks to each and every member, teaching and non-teaching, and all the administration staff of Vignan University for their kind invitation to me, so that I can come here and Vignan. Actually, I'm enjoying in Vignan University, and obviously I'm getting so much energy here to deliver my thoughts. And as I was telling, once again, I want to convey my special thanks, as I mentioned morning also, to Professor Devnara. And actually, for him only, I am here today. That initially I did not want to come here. I told that, okay, I will take all sessions in online mode only, but he insisted, sir, please come once. Really, I enjoyed actually. And so I am ready to come once again in near future to this Vignan University. Thanks, everyone. Now it's over to the coordinators. Madam, please.
Dr. Sujit Kumar Das, sir, thank you for being a part of our event. Your presentation was not only informative but also provides some practitionery on implementation of genetic algorithm by using Python. Sir explains how we have to get the maximum reliability with a minimum cost on multi-object to optimization by using different packages in a Python like NumPy, Pandas, and etc. And he also explains various concepts like fast non-dominated sorting by some different looping techniques. We are grateful that you are shared your experience and enthusiastic engaging the participants. Your expertise and insights on implementation of the genetic algorithm by using the Python captivated our participants and left a lasting impression on this FTP, on this faculty development program. Thank you for outstanding presentation, sir. We are grateful for your presentation and look forward to further opportunities. Thank you, sir. Once again, sir.
Thank you. Thank you.
All the participants, please fill the feedback form. It is available in the chat box form.
Okay, then, madam, I am leaving.
Thank you, sir. Thank you once again.